So welcome to this webinar. We are talking about Libra and the protocol specification of Chained BFT. And this is the part 4 of this webinar. So let's begin with the introduction video.
Remember when these were fast? And these? Technology has improved the world around us. So why is it simple to send one of these anywhere in an instant, but not money? What if we made money truly global, stable, and secure? What if everyone was invited to the global economy with access to the same financial opportunities? Introducing Libra, a new global payment system designed for the digital world, backed by the belief that money should be fast for Ope in Lagos, simple for Saul's family business in Manila, and secure for Betsabe when sending money home to Mexico City. It's powered by blockchain, making it safe and accessible, no matter who you are or where you're from. So join us as we move towards a world where money works for everyone. This is Libra, and it's just the beginning.
So let's move to the under the hood to understand this protocol. We are in the developer area, and let's see the repo of Libra BFT protocol. So this is the folder of Libra with some other videos that are different folders that have different implementations. So let's move to see interesting things of this kind of protocol specification. So the folder is the consensus, and this Chained BFT is one part of the Libra variant. The Libra variant is a variant of the HubSpot consensus protocol. So far, this consensus is calling HubSpot, that it's a leader-based Byzantine fault tolerance protocol, and also it's two parts of protocol. One, it's the basic HubSpot, that is the finalist commit, and it's very similar with the PBFT, that is the practical Byzantine fault tolerance, and has these phases that pursue the measures for finalize the block and commit the block. And the other part of this protocol is the Chained BFT, that basically is a PPA line that we saw in another videos that have a specific algorithm, and this kind of algorithm is for the generic phase and have a better connection with the things that the protocol has. So far, this PPA line is described in this figure that you can see here, and this figure is interesting thing for understand under the hood how to reach the consensus in a safety way. So let's move to see more interesting things under the hood for understand the protocol specification about Libra. So let's see. Let's open the Libra project. And this protocol specification is about the rotating process that we saw in another video, that it's a specification for the liveness condition. So let's see that condition. So it's calling the hub stuff, the linear optimal resilient watt measures. So it's open. So far, this was the first paper from the scratch from the hub stuff, and was the first describe of the protocol, and also the first implementation of the quality, and also the number of replicas and all the trade-off that have this protocol. So let's move to this liveness property. So we have two liveness properties, that it's liveness via synchronized clouds and liveness using a rotating processor. And this kind of protocol specification we can find here in the chain BFT in this part, in rotating processor. That is a structure of proposers and continuous rounds. So let's see under the hood this thing for understand what it's all about. So we are in live, you can ask me anything. So we have this this condition that is after GST. This GST means global standardization time. That is an interesting condition that have the topology network in the Libra protocol, and this topology network is the point-to-point. So far, this GST is an implementation for synchronize a level entrance for this kind of 2 delta using all broadcasts, because remember that you need to broadcast in a point-to-point setting. So this global standardization time help to make a better synchronous level in the delta that you need for brings us back to quadratic complexity. So far, this means that this liveness, it's a strategy for make a better resilient protocol out there. So we can see that this replica enters. So the replica under the hood is when you chain one node in the Libra BFT, and node act as a leader, but have trade-off of decentralization. That means that all not the propagation of the leaders are the same. So the decentralization in Libra BFT is wordless, or it's not too much in the propagation of the leaders. So this replica that it's in a topology network of point-to-point needs enter the next level upon receiving a proposal carrying a commit certificate for the previous level. So this kind of algorithm acts like a membership thing, and this commit certificate is for finalize the block committed, and the finality of this is to reach the consensus with a permissioned setting. So this certificate, it's in the query certificate, and this architecture that is the query certificate is for handle the data that you have. So if you have this query certificate, you can control why or what can join to your network. So let's see to this in the under the hood, this rotating meaning. So let's see here the code. So let's start with the structure of this rotating proposer. So this rotating processor, in the structure you have the proposers, that is a vector and handle the author. Then you have a continuous rounds in a protocol specification. So far, this is the struct of this rotating process, and it's a protocol specification for reach the liveness. That means live in the thing in a longevity way. So liveness is one condition that makes your network have a lot of longevity in the BFT protocol. And this Byzantine fault tolerance protocol are dealing with the partial asynchronous network. And this partial asynchronous network, it's a big deal for reach the consensus. And also we saw in another videos that exists the LP, that is the Fisher-Lasherton-Patterson impossibility, and this VLP impossibility, that also it's called in Fisher impossibility, is that no exists a non-deterministic way for reach the consensus in a synchronous network. So you need to find another way for no deterministic thing. So for this impossibility is the big deal for the asynchronous network. So you need to figure out a lot of things for these properties. So in this blockchain trilemma, the Libra-BFT is in the way of the scalability challenges and don't have a lot of decentralization. In the setup of the decentralization for the propagation of the leaders, so it's all about this permission setting. So let's move to see this function for choose the leaders. So you have this function, choose the leader. It's a point-to-point communication, so you need the vector of the author. So this vector needs another author for the peers that you have in this point-to-point communication, and makes sense in the way for the specification that they make here for this kind of transition that are handled different and rotation levels. So you need to spec different entropy here. So this entropy of the rotation of the levels is an interesting way for prepare to enter a rotation level. So it's an entropy that have in some way a long way. So this replica broadcast to all replica as synchronization measures. So this could be the measures in this representation. So in the function of choose the leader, you need to figure out a lot of things. So this pures into ether, it's minimum condition, and you spec no trust peers found. So in this entropy for find the transitions of the rotation levels, you are preparing to enter a rotation level in a one way. So you are only leading with the receiving f+1 enter measures for a level of the same measures that you are broadcast higher than its current level. So in this way start the replica echoes with on-enter meshes. So it's very confusing here, because in first way you have these rotation levels. That is a protocol specification that in a clear math works. Then you need to receive in the condition of any kind of BFT protocol, and then you need to deal with the trade-off that have all the BFT problem, that it's 2f plus 1. So if this is not working, the BFT protocol in the way to reach the consensus don't work. So it's basically here this scheme, it's to the rotation levels in the way for support the trade-off of the BFT problem here. So you have here, so let's implement the rotating process. So the implementation, rotating proposer is a function of new proposers that have a vector. Remember, the author is the ID thing, so you can replace here for ID, but this protocol specification use this kind of implementation. So this continuous rounds. So the self of the proposers and continuous rounds. And so far you have this implementation of this rotating process, and this way the proposers and the continuous rounds acts like the transitions rotation levels. So you have n, then 2n, then 3n, then 4n, and so on. So this is the continuous rounds. So you are dealing with one round, then this finalize, and when the round finalize you have your leader, and then change the view. Then change the view, you need to start in this loop sense again and again and again. So you need to have all replicas as synchronized meshes for reach the consensus in this partial asynchronous network. So let's move to choose the leader. So the peers, remember that it's a point-to-point communication, so you need the vector of the ID that here is calling the vector of author. So far this author needs the same expecting don't trusted peers found, so maybe could be a recursive here. So you have the peers. So then you need to make maybe here an implementation of the proposal election for these rotating levels. So you need to implement this in a payload sense. So the proposer election of the input that we saw in another video, that this T input is the state machine replication input that have a lot of conditions for the safety rules. So the safety rules and the state machine replication is connected in this input. So you expect that this proposer election is figuring out how to handle this SMR input, that is the state machine replication input. So let's move to for rotating proposer. You expect a function that it's valid proposer. So this self condition with the author so you need to handle here the continuous rounds. So let's move to see the venting here for the conditions. So if the self, get proposer of this round. See if you get the proposer of the round that you are figuring out. So it's good to be equal to author. So this could be a sound author, and else you have here unknown, and you have a pseudo code that could be better for this proposer election, but you are thinking in this condition of liveness for having the rotating processors in the way of the rotation levels. So it's interpretation here. So let's move to get these valid proposers, and then the function of the process the proposal. So you need to start then another round. So this function of get valid proposers will be equal of the same of all the inputs. So you're talking about the rounds, continuous round. So it could be a vector this of the self get proposer of some round. So forget this here. So maybe it could work like this. So it's boogie, still very boogie. Maybe you can put here something more conditions, but don't expect that this could be work in the first compile thing. So it's the hard part of the interpretation of any kind of protocol. So if you do this from the scratch, you do this paper, so you can understand more. But also you need the technical way for handle this. So maybe you cannot have all the expertise for run a good implementation of your protocol. So, but it's all about the related work that you have in the BFT problem, and also to do a novel BFT protocol. So let's process the proposal. So you need the same input. So you need to start to vend this. So far you have a rounds, but this round need to be specific for the state transition. So you need a ID way that in this protocol specification we are talking about author thing. So far this let round author could be a self get proposer for the proposer. So if some round author is different for the proposal author, so you only vend this. So you have the thing that you want to spec and the other thing that you you don't want to spec, so some proposals and debug this for the return that you spec. And so far you need the function of backend this, so back out the proposal for handle your data. So the round, have this round could be unknown. So far this is all about this rotating process. And in the test size, of course, you need to handle these rotation levels, and also see if these tests pass this test of this specification, that it's the BFT problem, that is the resistance for handle the protocol specification. So let's see the test. So you are testing here the rotating processor. So in the conditions you have different, choose validator, choose the ID, another validator, another author, the processor. So it's a way for make a randomness specification here. So you need to make a random test of this for figuring out if your code is working or your code is not working, and don't expect run all this in a one way. So you need to, for example, first this do the leader reputation, then the multiprocessor. So it's one test for one folder. So it's a long code here. So you need a big team for all the expertise that this have. So far, then this test Genesis, it's the current certificate. So you need to prove if this certificate for the Genesis is working properly, and basically it's only for dealing with the Byzantine failures that you can expect here. So this rotating process with 3 contingent round. So you are leading here with these 3 contingent round. That is this protocol specification. You have 1 round, then you have 2 rounds, but it's a cumulative rounds, and so on. So far this is only for echo broadcast. That is a thing that Bradshaw researchers. Bradshaw is a good researcher in the distributed systems. He works a lot in randomized protocol. He works a lot in distributed system algorithms. He works and he make a lot of technical terminology, and this is the echo broadcast. So this rotating contingent round, that is rotating different levels, have the same input for proof, and you need to finalize all. Then the last proof of this algorithm, it's the test fixing proposer, and you have all the things here, but you only think you only chain the rotating processor here, because you are choosing here a vector random of this. So it's a way for handling better data for the things that you expect here. So let's see more about this liveness property and finalize this video with this protocol specification. So essentially this echo broadcast of this liveness condition, that is the rotating processor, have different condition, and we need to read this. So after the global standardization time, if some correct replica obtains this, that is the BFT protocol trade-off, enter measures for the measures that you expect. This is the measures and the time here, that also is a specification. Then this echo broadcast, that is the rotating levels. A scheme guarantees that be a time of t plus 2 delta times and all correct replicas obtained to after enter measures for xn. So if this echo broadcast test works, you have the guarantees of these 2f plus enter measures for the enter measures that you have. So this is the hard thing for figuring out how to have these enter measures in the condition of the 2f plus 1, and in order to guarantee progress for level whose processors are faulty. Open entry level ELF, a replica sets a time of 4 delta. So you put more hard thing here. So if you expect here in 2 delta, why not in a 4 delta? So you double the delta. So if the time expires without receiving a proposal, a replica, remember that the replica, it's all about to spread the measures across this PBFT communication. And this PBFT is the practical Byzantine fault tolerance. We can see here this first figure about this kind of implementation for understand how the replicas start. So this was a paper writing by Castro and Barbara Lipskop. It's an incredible paper. So this is the first paper that introduced the practical way to reach the consensus, and let's make a review of this. And this is the normal case operation. So in this way, this practical Byzantine fault tolerance is divide these spread measures in different parts of the protocol. So then you have these requests, prepare, commit, and then the reply. So it's an interesting thing for handle any kind of measures here. So far, this replica prepares to move to the next level. So for move to the next level, in this way, need this rotating processor that needs the enter measures for the level that you are handle. So this is the rotating processors algorithm. That it's the same thing that we saw in the code, but in a beacon way. So it's only a algorithm for handle this rotating process. So this algorithm is functionally a replica. So upon a measures of this, process all this input that is very similar of the input that we have in the code, in this input. The peers, the vector, the author, the proposal election, the mood self, and the proposal blocks, And so far, this it's for the condition that this kind of protocol has. So this kind of algorithms are very hard for understand the perspective of the BFT problem, but have a lot of sense if you code and then test this kind of protocol specification. So this pre-enter, and then the measures that you are trying. So for a level of any kind of this proposal, pre-enter the condition here. So you move for both these digest, unit digest, debugging this data, and then omitted for brevity, retry missing commands as need, update the high current certificate, that is a certificate, and the title, all the things that these measures have. So remember that is the beacon implementation. Then you have here upon pre-enter, so this is when I start the rotating levels here. So then you need to modular this for send the message to all replicas, and then enter L. So this is when I start the echo broadcast, that also is calling the brush echo, and it's when the meshes start to spread across all the phases, and it's a normal case operation in the practical way for reach the consensus. So then when this Racha echo or broadcast echo encodes works, you put these meshes and enter the same way. Then you spec entropy of the deltas of the type, then it's a left safe and saves entity last rotation level L level. You need to handle this. So you can see that this echo broadcast also have derivative and enter the rotation level that this protocol specification is, and then finalize this with the level that you have. You handle very well, and this rotating process works as you want. So the condition, if the replica process for this level with the input it's working, then send all this high tail, and you finalize for committed the replica for the next phase of this hop-stop protocol. That it's very similar for the practical Byzantine fault tolerance, but has this topology network in a point-to-point. So it's very different in so many ways. So let's move to see more things about this rotating process, and we can see here the liveness proof of these two kind of algorithms. So there are lemmas and their proof, and are very specific in all the things that could happen or not could happen in the protocol specification. So you can deep dive a lot of these kind of lemmas. It's all about the global standardization time, what happens if the 2 delta period is very entropy for the double of the time, that is the 4 delta. It's interesting thing. So we continue in another video for this rotating process. I think my time is over here, so let's see you in another time, and have a good day.